So the air that we breathe is a mixture of gases. Oxygen, nitrogen are the main ones. And our lungs perform best when the partial pressure of oxygen is 0.21 atmospheres, which is what the pressure is at sea level in air. At higher elevations, when you go to high elevations, the atmospheric pressure, the total pressure is less, and so the partial pressure of oxygen is also less. Because if oxygen is 21% of the composition of air, then it exerts 21% of the pressure. When the total pressure decreases, the pressure of oxygen decreases also, and we can't breathe as well. You go to very low levels and you get hypoxia or oxygen starvation. Hypo means low or less, below, so this is a low level of oxygen. Severe hypoxia below 0.1 atmospheres may result in death. Makes sense. You don't get enough air. If you don't get enough oxygen, you're going to die. You can also have too much oxygen, as with many things, even things that are vital for life like water. Too little will kill you. Too much will kill you. Same thing with oxygen. So too little, hypoxia, is bad, but you get too much oxygen, you get oxygen toxicity. That's also bad. Thankfully, there's a wide range that's safe. So above about 1.4 atmospheres, you can have symptoms of oxygen toxicity. Those symptoms include twitching, tunnel vision, and convulsions.
Hypoxia is at 0.4?
You don't need, hypoxia is below 0.1. I'm not going to test you on those numbers. It's more of a, why would this matter to everyday life kind of a thing. Or to scuba diving. So how could you get oxygen toxicity? Well, one thing would be if you were breathing pressurized air, which is most likely to happen when you're scuba diving.
Is that what the bends are?
The bends have to do with nitrogen.
Oh.
And we can talk about that too. At the surface, the total pressure of air is 1 atmosphere, and so you've got 0.21 atmospheres, partial pressure of oxygen. Things are perfect. When you go below the surface of the water, because the pressure of the water on your lungs would make it impossible for you to breathe at 1 atmosphere, you need to have pressurized gas so that you can still breathe. So down at 30 meters, the total pressure would have to be 4 atmospheres, and so you would need, you would be getting 0.84 atmospheres of oxygen. Now that's not high enough to be dangerous, but we're getting up there. If you went very deep and were breathing just pressurized air, you could get oxygen toxicity. There's a little blurb in the book and a picture. I remember watching Flintstones, the cartoon, when I was growing up, and they would hide in the lake and they'd breathe through a reed, right? Have you ever tried doing that? It's really pretty hard. And if you were to go to any depth doing that, snorkeling works close to the surface, but if you go too deep, even if you had an open tube to air at the surface, you wouldn't be able to breathe because the pressure of the water wouldn't allow you to expand your lungs. When we have pressurized air, we also have an increased partial pressure of nitrogen. And too much of that gives you nitrogen narcosis. It's called rapture of the deep. Feels similar to being tipsy. You're like, well, maybe you like being tipsy. Well, impaired judgment, 50 meters below the surface of the water is probably not a good idea. And that's where some of those, especially the earlier divers, when they didn't understand some of these things, they go down there and they would just do what seemed like really dumb things. Like, they killed themselves and they went the wrong direction. They went down instead of up or something. Well, their brains weren't working properly because they weren't getting the right combination of oxygen and nitrogen or other gases. So if you go deep sea diving beyond 50 meters, it's important to use a specialized mixture of gases so that you don't get too much nitrogen and you don't get too much oxygen. Heliox is one mixture. It's a mixture of helium with oxygen. Now, helium is not something that we can breathe and have it sustain us, but it's also not going to harm us. And so that's why they stick helium in there. It also makes you talk like Mickey Mouse, but since you can't talk when you're underwater, nobody knows.
It doesn't kill brain cells when you do it?
It doesn't kill brain cells. Okay, so if you got helium and no oxygen, the lack of oxygen would kill brain cells, but the helium would not kill brain cells. And in terms of breathing gases other than air, helium is fine as long as you remain upright. If you were to breathe helium upside down, helium is lighter than air and it's going to stay in your lungs and it won't come out. And then that could cause a problem. So heliox can avoid nitrogen narcosis and oxygen toxicity. So let's do a problem with this. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres, the ideal pressure. What must the total pressure be? Well, let's go back real quick. What we were talking about, well, maybe it's not so quick, over here. The partial pressure of a component is equal to the fractional composition of that component times the total pressure. So the partial pressure is going to equal the fractional composition times the total pressure. And if you understand percentages, oops, I'll just cross that off. There's got an extra U in there. That's just ugly. Oh well. 5% of this mixture is oxygen. That means oxygen exerts 5% of the pressure. So we want 0.21 to be 5% of the total pressure. Here we want to find out what the total pressure is.
Would you multiply both 1.20 to get 100% and then?
No, you don't need to multiply. You don't want to get 100%. What we want to do is we want to convert this percent into a fractional composition. So you take the 5%. I had a new stylus and I left it somewhere. 5%. So you're going to divide that by 100, and that will give you the fractional equivalent of 0.05. So we want 0.21 atmospheres to be equal to 0.05 times, well, I don't need parentheses there, times the total pressure. 5% of the total pressure. So the total pressure then needs to be 0.21 atmospheres divided by 0.05. It's 4.2. So you'd want the total pressure that you were breathing of that gas to be 4.2 atmospheres. So what divers will do is they'll have two different kinds of gases, because as you go down deeper and deeper and deeper, you need a different mixture. You need a different pressure. But, well, you need an increasing pressure, but you may need less pressure of the one containing oxygen, and so you can vary the ratio of the different gases that you're breathing. It's a lot more complicated than you might think. It's like, oh, well, you just put a cylinder of compressed air on your back and you put the mask on and you dive, right? It's more complicated than that, and that's why they make you go through all those classes and get certified. Personally, being that far underwater makes me feel claustrophobic, and I have absolutely no interest in doing that. Collecting a gas over water. We did this in lab yesterday, although our setup was a little different. We used magnesium instead of zinc, but we reacted a metal with an acid and we got hydrogen gas. Here we're allowing the hydrogen gas to escape through a hole in the stopper into this tube, and we're directing it into this jar that's inverted. It was filled with water. As the hydrogen bubbles in here, it displaces the water. And so we have hydrogen gas that's trapped here. It has to go in here. It can't escape anywhere else. We also have water molecules in the gas state because the water here will begin to evaporate as soon as there's any space for it to evaporate into. And like we talk about in chapter 12, you've got this rate of evaporation, and then once you've got some water molecules here, so we have a rate of evaporation and a rate of condensation. Those eventually become equal, and we get this vapor pressure of the water that depends only on its temperature. So we have water vapor here, and we have the hydrogen that we're interested in. We call that a wet gas. So if we want just the pressure of the hydrogen, we need to subtract the pressure of the water. That depends only on the temperature of the water where the gas is being collected, and so we just look it up in a table, something like this. So here's the vapor pressure of water. This is not nearly as detailed as the one in the CRC we looked at yesterday. These are not things you would memorize. They would be given to you if you needed them. But if you notice, as the temperature increases, the vapor pressure of water increases. And if you keep going, when you get to 80 degrees Celsius, the vapor pressure of water is 760 millimeters of mercury, and it begins to boil. So we should be able to do questions like this. Hydrogen gas was collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen gas? Well, Dalton's law of partial pressure says that the total pressure is equal to the partial pressure of each gas added together, the sum of the partial pressures. So the partial pressure of hydrogen must be equal to the total pressure minus the vapor pressure of the water. Total pressure here is 758 millimeters of mercury. It's important to put your units because like yesterday, the barometer measures the total pressure in inches of mercury. And when you look it up in the table, it's millimeters of mercury. And when you subtract those, you get a meaningless number because you can't subtract inches or millimeters from inches. So we look at the table and we find the temperature that we have. 25 degrees Celsius. So that tells us that the vapor pressure of water is 23.8 millimeters of mercury. So we got 758. Turn the calculator on. 758 minus 23.8. Vapor pressure of the hydrogen is 734.2. And then we need to look at sig figs. Subtracting, we're looking at where the number ends, where the last sig fig is. So here it's in the one place, the ones place, and here it's in the tenths. So we'll round this to the ones place and call it 734. Any questions? The pressure of a component always has to be less than the total pressure.